and establish some of the basic properties of the derived category of complexes of sheaves. Now, like everything else that I've been doing, most of what I say uses only the formalism of abelian categories. But today we are going to get one theorem which involves Flabby sheaves and therefore is not a statement in the arbitrary abelian category. So anytime you hear the word Flabby sheaf, that's a clue that, because that doesn't have a formal definition in the abelian category language, it's something about sheaves. And so there's going to be one theorem, the fundamental theorem of sheaf theory, that is not part of the general discussion of abelian categories. But with the exception of that one theorem, and any time I mention Flabby, everything else uses only the language of abelian categories. So we're going to start with a category which is the category of complexes of sheaves on X. Sheaves, and remember these are sheaves of abelian groups. On X. So a category, an object is simply an indexed collection of sheaves, and these maps satisfying d squared equals 0. Map of sheaves. Now there are various and the morphisms from a complex A to a complex B is simply a collection of maps Fn, morphisms of sheaves from An to Bn, satisfying Fn compose D, that would be D in B, is D in A, compose Fn plus 1. Chain maps. So morphisms of sheaves that give maps of the complexes. Okay, so that's the category. There are some subcategories that we will carry along at each step of the process that have fairly standard terminology notation now. Complexes with a plus means bounded below. Complexes with a minus mean bounded above. And B means bounded. So okay. So that's the category of complexes of sheaves. And of course, associated to a complex of sheaves to an object, we have its cohomology sheaves, which I'll denote this way, the cohomology sheaves. All right, so this is just a graded, well, it's just a collection of sheaves indexed by the integers, so a graded sheaf. Its kth cohomology is simply the kernel of AK into AK plus 1 over the image of AK minus 1 into AK. And this is a sheaf over the space X. So sometimes called the cohomology sheaves, sometimes called the local cohomology. This allows us to introduce a notion which won't be important for a while, but since it already exists at this level, I'll introduce it and we'll see it coming up later in the talk. Morphism morphism is a quasi isomorphism if the induced map on homology, on these local homology groups, sheaves, is an isomorphism. Okay. So an example of some of these objects in quasi-isomorphism, a sheaf A is naturally a complex. You would put it in degree 0 typically, but you could put it elsewhere if you wanted. So it makes a complex with only one non-zero term, the sheaf in degree A. In that case, the cohomology sheaves, well, nothing much happens. It's A in degree 0, and it's 0 otherwise. And what we've been calling a resolution of a sheaf, which was a complex somehow associated with A, is an example of a quasi-isomorphism. So I've been writing resolutions this way. So from before, this is a resolution of A. Maybe I should say recall. Is a resolution of A if this whole longer augmented complex, if star is exact, which recall means has no local cohomology, no cohomology, trivial cohomology sheaves. So at each stage in this extended complex, kernel equals image. Well, we can bend this around a little bit and view this as a quasi-isomorphism between this complex in degree 0 and this complex in non-negative degrees, where this is the map rho, and these are, of course, the 0 maps. This is a quasi-isomorphism. Those are the same statement. So a resolution of a sheaf, as we've been talking about it to date, is simply a quasi-isomorphism from the complex made up only of the sheaf in degree 0 to the thing that's the resolution. Right? Okay. Yeah. One operation that, again, will be important later is the shift operation. So if you have a complex of sheaves, there's a new complex of sheaves, the shift by 1, and it has the property that sheaf in degree n is simply a n plus 1, and the differential from the sheaf in degree n to the sheaf in degree n plus 1 is minus 1 to the, well, is minus d. Okay? I found this notation very confusing. I want to try to explain it. Okay? And one reason it's very confusing is you put this guy on the right in the notation, but it's really on the left. So that's one thing that's confusing. The other thing that's confusing is this looks like you should take A and shift it up 1, right? But in fact, what you do is you take A and you shift it down 1. But this is the natural notation, even though it's a little counterintuitive. The way to remember it is these two numbers add up to that one.
Or you could just say n minus 1 equals a n, and then it would be clear that it's shifting down. No, not there. The n minus 1 outside.
Yes, that makes it clear that I've taken an
Right.
and I've shifted it down into degree n minus 1.
So this complex with one term shifted by 1 will actually have a component degree minus 1.
That's right. So let's think about Z is the constant sheaf in degree 0, and this is the sheaf, the complex where this is degree 0, and this, of course, is degree minus 1. Okay. You shift down. Okay. Now, why the minus sign? Well, that's because this symbol 1 is actually a right action of something. So A1 is naturally Z1 tensor A. Because Z1 is simply a copy of this free thing Z shifted down 1. If you tensor with a free thing, you just get back what you started with, but the shift has occurred here. Right? And now it's clear what is D of, let's call the generator of this thing eta, which is degree minus 1. Right? Local section. Tensor an element here in A. Well, this is like topology. Anytime you permute two things, you introduce a sign which is the product of, is minus 1 to the product of the degrees. So this should be minus 1 to the degree of D times minus 1 to the degree of eta tensor dA. Because, I mean,
That would be minus 1 to the sum of the degree.
Minus 1 to the product.
That's better. Thank you.
And you have an equality sign that shouldn't be.
Now, secretly I use something else, which is the d of eta is 0. But that's an issue. D of eta is 0, so that's why there's only one term. And of course, D is a derivation, it's degree plus 1, and eta is degree minus 1. So this is minus eta tensor dA. So when you suppress the eta, you've changed the sign of the differential. Okay? All right. And of course, if you took A, you could take A and you could shift it k times, just iteratively shift once, one k times, and then D becomes minus 1 to the k. Okay. All right. All right. Now I want to talk about the Hom sheaves and the global Homs. This is sort of interesting. And I've also found this somewhat confusing in the beginning because there's so many different things Hom could mean. So recall that if you have two sheaves, Hom AB, this is the sheaf Hom. Okay. And it associates to an open set. So Hom AB on an open set U is simply the global homomorphisms, sheaf homomorphisms, from A restricted to U to B restricted to U, which is not Hom AU in general, BU. It's much more subtle than this. It's the homomorphisms between these sheaves over U as sheaves. That means for every open subset of U, you have a homo. So in fact, what it is, it's collections of FV mapping AV into BV over open sets indexed by open sets V and U, compatible under restriction. as you pass from one V to a smaller V. So it's all these commutative square diagrams. That's what this thing is. Yeah?
I'm a bit confused because if you had a homomorphism from AU to BU, wouldn't you have, by restriction, compatible homomorphisms?
Well, it depends if you had this.
Yeah, but if you had
If you have this,
things like that,
these are abelian groups.
that's true, but you have restriction maps.
Yeah, but
This is part of the whole structure.
that's,
Okay.
yeah, so I have restriction maps from AU to AV and BU to BV, but
Right.
why should they factor? You have to give all the factorizations. Yeah.
I'm a little confused as well.
Uh,
I thought you were giving the definition of the sheaf of the sheaf. Is this a circular definition?
no, no.
There's a script in the home of the left.
Oh.
Yeah. So this is the morphisms in the category of sheaves over U between these two sheaves. And now so this is global homomorphisms, but only over U. And this is the sheaf homomorphism.
Is there a difference in the notation or something?
Yeah. This is supposed to be Roman, and this is supposed to be calligraphic. You know, it's like this is the local sheaf cohomology, and this, and sometimes you even do this, is the global cohomology. So it's supposed to mimic that. These are global things, and this is the sheaf. So this is, as I've defined it, a pre-sheaf, because to each open set I told you what it was, but it's an exercise. I think I've talked about this before. This, in fact, is a sheaf. So it satisfies the sheaf property, and so the global sections of Hom AB, global sections of this sheaf, are in fact the global homomorphisms from A to B, and these are the continuous maps étalé F between the étalé spaces. Continuous and additive on each stalk. The collection of continuous maps. So those are the global sections. Okay. Well, that was for single sheaves. Now we want to talk about Hom between complexes of sheaves, and this will be a complex of sheaves. So A and B now are complexes of sheaves, and I want to define a new complex of sheaves called Hom, and this little dot is to indicate to you it's a complex, A and B. So Hom K of A, B is simply the sheaf is the sheaf Hom between the A's and the B's that shifts degree by K. So this is the direct product over N of Hom A N plus K into B N. So Hom 0 would be degree preserving, the sheaf of degree preserving maps. Hom 1 would shift up. Sorry, got this backwards. So the degree of a homomorphism is the amount it shifts the index. Positive degrees shift up. All right. And the global sections of Hom K, A, B are simply the product over N of the global homomorphisms from A N to B N plus K. Okay. Now there's a differential here. This is a complex of sheaves, and when you take global sections, you get a complex of abelian groups, namely the differential is supposed to go from Hom K AB into Hom K plus 1 AB. And it's defined, I'll just write down the formula and then maybe say a few words about how to interpret it. So here's the formula you should remember. D of F of A should be dF of A plus minus 1 to the degree of D times the degree of F of dA.
John,
Yes?
does in general the global section functor commute with infinite products?
Yes, it does. Yeah. I mean, the stalk is not the infinite product. That's a little subtle, but the global sections do. So here you're supposed to understand this formula.
What is the degree of capital D?
That's 1. So that's plus 1.
And by definition?
Well, it goes from k to k plus 1.
Oh, okay.
So you can interpret this formula in terms of local sections over here. I mean, it makes sense. It's a completely general formula. It makes sense over any open set U. It's compatible under restriction and so on. So it really is defining a map from this sheaf to this one. Okay? And again, we see the sign rules. So what this says is that dF of A is d of f of A minus 1 to the degree of f of dA. Okay? So let's unravel that in the case when the degree of f is 0. So what's the condition that df equals 0 means? Well, I claim the condition for a map of degree 0 to be a cocycle, df equals 0, simply means that f is a morphism in the category of complexes of sheaves. Because what does the formula say in this case? df equals 0, so df A equals 0 is d of f of A minus degree of f is 0, f of dA, i.e. d of f of A is f of dA. F commutes with the differentials. So the morphisms, well, I guess where am I working now? I guess if I work, let's work in the global section. So let's work in Hom 0 A B. So in this, the cocycles are morphisms from A to B. Okay. What are the coboundaries? Anybody want to guess what they are? Chain homotopies. So now we have a degree minus 1 element is a map, let's call it H, from AN, or collection HN, from AN to BN minus 1. And the differential of a collection like this Well, now the sign is D plus. So it's DH plus HD. The sign changes because the degree of F is now 1. Okay. Well, this is for any collection of maps from the sheaves A to the sheaves B shifted down by 1. If you form this expression, it is a morphism of sheaves. This is a morphism from A to B, a morphism. D squared is 0. I didn't check that, but it's the usual sort of exercise with the signs. D squared is 0. So this will satisfy the co-cycle condition automatically, and therefore it will be a morphism, and this is what we call a chain homotopy. So H is a chain homotopy. And now we see the zeroth cohomology of Hom A, B is simply chain homotopy equivalence classes of morphisms A to B. Okay? I guess I didn't say chain homotopy is an equivalence relation. If you have two different chain homotopies, one from F1 to F2 and one from F2 to F3, the sum will be a map that lowers degree by 1 is a chain homotopy from F1 to F3. Okay. So that's the transitivity. What is HK of Hom A to B? Well, this is simply the homotopy classes. So I'm going to use now this for chain homotopy classes of morphisms. It's simply the chain homotopy classes of morphisms from A to B, K. I hope I have the K in the right place. Let's see, I want to go from A n to B n plus K, and I have the K in the wrong place. And this is A K. AK in degree n is A n plus K. Yeah, so I had it in the right place. Right. Which is B n plus K. So they're maps like this, commuting with the differentials up to chain homotopy. Okay. So this now allows us to define the homotopy category of complexes of sheaves, which usually has the name K, and of course it can be adorned with plus, minus, or bounded of X. This is the homotopy category. Of complexes of sheaves. Bounded above, bounded below, bounded. So the objects are simply complexes of sheaves, same objects as before. And the morphisms now are the homotopy classes. So the morphisms in K from A to B are the chain homotopy classes of ordinary morphisms from A to B. So it's a homotopy category in the usual sense.
So we don't want to identify the complex of sheaves by F quasi isomorphism.
No, it's not here.
What happened to this index K?
What happens what?
This index K here.
Oh, well, this only is recording H naught. So I'm not using the other cohomologies at this point. Okay? So it's not true at this level. If you have a quasi isomorphism between objects in K, it's not true it has a homotopy inverse. It is true that quasi isomorphic things are isomorphic in this category, but that requires more work. Okay? And that's where we're headed. Okay. So the first theorem, which is related to, now so I'm going to state and sketch proofs of several theorems which are about complexes of sheaves. Each one of these I've already proved for an individual sheaf, but I haven't proved for a complex of sheaves. So the first is every A bounded below has an injective resolution. And again, it can be bounded below. Okay. I don't believe this is true without assuming bounded below. In fact, I'm almost positive it's not. So if you have a complex of sheaves bounded below, in fact, I'm going to embed it in an injective complex of sheaves bounded below in the same degree, bounded below at the same degree. Okay. And then we'll talk about theorems that that address the issue of uniqueness of this resolution. All right, well, just for simplicity of notation, once the sheaf is bounded below, I might as well assume it starts in degree 0. Okay. So here's my complex of sheaves. Okay. I guess I want to go up, so let me give myself a little room. All right, well, I know that the sheaf A naught embeds in an injective sheaf. That's the basic fact. I want to try to extend across here. I'm just going to make one row that's the injective resolution of A. Okay? So that's the start. Now I have to consider I naught cross over the kernel of, if I cross over A naught, A1. Let's call that J1. That's our first approximation. This argument's going to look very familiar. Okay. So take the fiber product of I naught and A1 over A naught. And I need to study now the maps I naught into J1 and A1 into J1. In particular, understand their kernels. Well, this one first. Since A naught embeds in I naught, A1 embeds in J1. So this is actually an embedding. The kernel of I naught to J1 is the kernel of A naught to A1 under the inclusion from A naught to I naught. Okay? And now I embed these, I embed J1 in an injective sheaf I1 and just take the composition. So this will be an injection, and this will be a map that has the same kernel as this map, which is identified with the kernel of A naught under the inclusion. So this So far, this map induces an isomorphism on the zeroth cohomology sheaf, because the zeroth cohomology sheaf here is the kernel of A0 to A1. There's no image. And the zeroth cohomology sheaf here is the kernel of I0 to I1. Again, there's no image. And they're identified under the inclusion. The extra piece of information I need from this fiber product diagram is that if you take the image of I0 in I1 and you intersect it with the image of A1 in I1, so the image of this intersect the image of this is exactly the image of A0 into I1 going either way around the square, which is a commutative square. And that's because the image in I1 is really the image in J1, and anytime you take a fiber product, the image of this one intersect the image of that one. So in this fiber product, the image of this guy intersect the image of that guy. Well, you have something in here that can be written as 0A, and it can also be written as I0. That's to say it's in this image, and this is to say it's in this image. Well, if these are equal in the fiber product, that means there has to be an element in A0 that goes here and also here. And therefore, you're in this image. Okay? So that's the inductive step I need. I'll do one more, and then you just push it forward. So now I'm going to take, where shall I do it? I'll do it over here. Now here I'm going to take I1 mod I0 fiber product over A1 mod A0 with A2. I'll call that J2. And I need to study the map I1 mod I0 to J2 and A2 to J2. Okay, well, I claim A2 to J2 is an injection. For that, I need to know, what do I need to know? I need to know this injects here. If this injects here, then this injects here. Well, I need to know that if I start with an element in A1 and I push it into I1 and it goes to 0, that is to say it's in I0, it actually comes from A0. That's exactly this fiber product statement. So this is an injection, and therefore, so A1 over A0 injects into I1 over I0 by this assumption, where did I write it? By this assumption. And therefore that implies the standard argument that this thing injects. Okay. And now what about this? Well, the kernel of this, exactly as before, the kernel of I1 over I0 into J2 is identified with, under the inclusion, the kernel of A1 over A0 into A2. Well, this is the cohomology at level 1 for the complex A, and this is the cohomology at level 1 for the complex I, and they're identified. So, well, that's for J2, and then, of course, I embedded J2 in an I2. So the cohomology in degree 1 here maps isomorphically the cohomology of degree 1. I still have the fiber product statement. The argument just pushes in front. These are, of course, by construction, all injective. So that's the proof that every A has an injective resolution. Any questions about that? I mean, this is very similar to the arguments I was giving you last time. I mean, we see this over and over and over again. Okay. All right. This now allows us to define the cohomology, the global hypercohomology of a complex of sheaves A. It is the cohomology of the global sections of an injective resolution with the map induced by D for I, D, and injective resolution of Well, that's not a very good definition unless I can show this is independent in some of the canonical isomorphism of the choice of injective resolution. And so that's what the next theorem is about. We have a complex of sheaves. We have some resolution. So I is a resolution, that is a quasi isomorphism. And I is an injective resolution. And there's a morphism of sheaves, the complexes of sheaves, phi here. That's the injective resolution. So that's the hypothesis. Okay. Then there exists a morphism rho from this resolution up to I. And a chain homotopy between I compose rho and the original injective resolution phi. Furthermore, rho is uniquely determined by these properties up to chain homotopy. Okay. So you can factor this injective resolution through any other resolution up to chain homotopy, and this factorization itself is unique up to chain homotopy. Okay.
What is the resolution for a complex?
It's some other complex and a quasi isomorphism.
It's not, itself is not acyclic.
No. It has the cohomology sheaves that this has. Right. Well, let me just show you how this, well, one consequence of this is that this is a reasonable definition of the hypercolomology of A. So, corollary, if we have two injective resolutions, then there exists I mapping maybe I to J, and J a morphism from J back to I, so I and J, such that J is equal I inverse in K plus of X. Okay. So these objects and I and J are uniquely determined. To make the diagram commute. Up to chain homotopy, of course. So remember, K is homotopy. K is the homotopy category. Sheaves, but morphisms are homotopy classes. So I now have I and J are homotopy inverses, chain homotopy inverses of each other. That is, in the homotopy category, they're inverse isomorphisms, and both make this diagram commute up to homotopy, and therefore commute in K plus of X. And the proof of that, let's start off with our two injective resolutions, phi and rho. Apply this theorem using the fact that this is injective to produce J, making the diagram commute up to chain homotopy. Apply the theorem using the fact that J is injective to produce I. And of course, J compose I satisfies the diagram where you have rho mapping to J and rho mapping to J. And that map is unique up to chain homotopy, therefore J compose I is chain homotopic to the identity. Same argument. I compose J is chain homotopic to the identity. Okay? And J followed by I is chain homotopic to the identity J. And the diagram commutes up to chain homotopic. So that's exactly this statement. And they're unique. Okay? Well, a further corollary of that is that the cohomology of the global sections of I, under the same hypothesis, is identified with the cohomology of the global sections of J under its D. Because I use these chain homotopic maps between complexes of sheaves, induce chain homotopic maps on the complexes of global sections, and therefore the complex of global sections here and the complex of global sections here have homotopy, chain homotopy inverse isomorphisms, and therefore their cohomologies are identified. Okay? So this is a reasonable definition of the hypercolomology of a complex of sheaves. In fact, the theorem I'm going to prove, well, this is the theorem I'm going to prove. If you have a quasi isomorphism and an injective resolution of 1, you get an injective resolution, a quasi isomorphism and I'm going to prove a more general statement. So, theorem slightly stronger. Suppose that A to R is a quasi-isomorphism, and I is an injective sheaf, is an injective complex. Okay. Then I star maps the homotopy classes of maps from R to I into homotopy classes of maps from A to I is an isomorphism. And this is the special case when the map, well, you're studying a map which is a resolution. Okay. Okay. Actually, a corollary of this theorem is that if F mapping I to J is a quasi-isomorphism, between complexes of injective sheaves, then F has an inverse in K plus of X. So these are sheaves bounded below. So apply, well, this is an injective, well,
Confused about something, because that statement would be saying that injective resolutions are both fibrant and cofibrant, because you have this isomorphism.
yeah.
And that's what you want to say, or just that are fibrant and you only have a map?
You worried about this?
That the fact that there's an isomorphism between those two.
Yeah.
Because then you can have this diagram starting with rho, and then you can complete the phi. And everything.
Yes. Yeah.
Uh-huh.
Right. No, it's an isomorphism here. Yeah, you can put it, it doesn't matter which way the quasi-isomorphism goes. So let's apply, in fact, that diagram. This is an injective resolution of I. How do I do it? Yes, and there. How do I apply this diagram? J. How do I apply this diagram? Let's see. I have I to J. Well, about the only thing I can do is take I to I. No, but that.
Isn't that your diagram with the...
Yeah, so this is injective, and this is a resolution. Oh, but now the map goes this way. So maybe this is an injective resolution, and this is a resolution. So I get a map like that, so that this diagram commutes up to chain homotopy. So that's the chain homotopy inverse for this guy. All right. Okay, well, I think I'll prove this version of the theorem and not that one. And in fact, I'll only prove half of it. I'll construct rho and show a chain, construct rho so that this, and a chain homotopy from this composition to phi. I'll leave it's unique up to chain homotopy to U. It's a very similar sort of argument. So we're going to try to prove this theorem. So what have we got? We'll start A0, A1, A2, 0. And I have phi to I0, I1. So this would be phi naught, phi 1, phi 2. Okay. And then I have I to R0, R1, R2. Okay, I want to try to define rho across here and a chain, rho naught, and a chain homotopy to get started. Well, the first thing you know is that the kernel of A naught maps to the kernel of, well, when I write kernel A naught, that's my shorthand for the kernel of the differential from A naught to A1, okay? And this will be the shorthand for the kernel of the differential from R naught to R1. This is an isomorphism because this is the zeroth cohomology of A, and this is the zeroth cohomology of B, and this is a resolution. Okay? So we define rho naught on kernel R naught to make the diagram commute. Okay, so there's a unique map, rho naught, at least defined, well, rho naught so far is defined on the kernel of R naught in here. Okay? Does the diagram commutes? Okay. Well, this is an injective sheaf, so you can extend arbitrarily, extend rho naught on kernel R naught to R naught to rho naught, mapping all of R naught to I naught arbitrarily. Okay. But it will still induce an isomorphism from the zeroth cohomology here to the zeroth cohomology there. Okay. Now I need a chain homotopy. Now let's construct the chain homotopy. This is going to be a map H from A1 into I naught.
That you're using the injectives are Flabby, something like that?
No, I'm using the categorical property of injectives. Given a morphism on a subsheaf, it extends.
Right.
It's the categorical property. Okay, so now I need a chain homotopy from A1 to I naught. So let's think about this. Let's take the difference, phi naught minus I rho naught is a map from A naught into I naught. Okay. But it vanishes on the kernel of A naught, because by construction the diagram commutes on the kernel of A naught, and therefore the difference vanishes. All right. And then I can go by, well, I can go by D, so A naught mod kernel A naught goes by D into A1, and that's an injection. So I have a map. This difference gives me a map from A naught mod kernel A naught into I naught. A naught mod kernel A naught embeds into A1, and therefore I can extend the map to a chain homotopy H. And so extend so find an H. So then find H, mapping A1 into I naught, such that DH equals phi naught minus I rho naught. And that's exactly your chain homotopy. Chain homotopy is supposed to be DH minus or plus HD, which is 0 in this case. Well, shall I continue? Maybe I'll do one more step. But yeah, this is a slightly different, one extra condition. So suppose inductively, so what I'll do now is I'll use this chain homotopy to vary phi by chain homotopy until it agrees with I rho. So the inductive hypothesis is I have rho naught up to rho k, and I compose rho is equal phi, 0 less than or equal r less than or equal to k. Right, so ak, phi k, that's the last one, ik, this doesn't change, rk, rho k. So I have commutative diagrams here. So that's what I have. So up to here, I've constructed rho, and the diagrams commute, and then I have this piece of a diagram at the next level, and I need to try to construct the rho k plus 1 and a chain homotopy. So this is what I need to construct. Right? Okay, well first, let's consider the map from image AK inside AK plus 1. I don't want to do this. Let's consider kernel AK plus 1 over image AK. So the K plus first cohomology. And this maps to kernel of RK plus 1 over image RK. That's an isomorphism. And let me see. And let's map all of this into IK plus 1 mod image IK. I'm sorry, I'm not. No, I think I want kernel here. So I have the map from the cohomology here to the cohomology here. This cohomology is isomorphic to the cohomology of A, and therefore I can define a map from kernel over image here so that this diagram commutes. So this will be an isomorphism. What I'm trying to do is I'm trying to extend the map from the kernel of RK plus 1 to the kernel of IK plus 1 so that the diagram cohomologically commutes. I'm sorry, I'm getting confused. Let me look at my notes. All right, here's what I said. I said the map from RK into IK goes into IK plus 1. And this factors through RK mod the kernel of RK into here. Right, because the kernel of RK maps to the kernel of IK and therefore goes to 0 here. So kernel RK goes to 0. So under this map, it'll factor through the quotient. Okay, so there's a map from, and, okay, RK. This embeds into RK plus 1. So I can define a map from RK plus 1 here so that this diagram commutes. So I can, the first thing I do is I define a map here for OK plus 1 so that the R to I diagram commutes. Next I want to arrange that the kernel of RK plus 1 maps to the kernel of IK plus 1. And there's no reason to expect that I'll have that from this construction. I think I should think about this and get back to you next time rather than try to sort out this argument. Yeah, let me just do this argument next time because I'm more confused than yeah, I'm just confused about it. So let me say what we've done. So I'll put this statement aside. I'll come back to it. So what we have is, given all these theorems, we have two models for the derived category. One is complexes of sheaves up to homotopy. So the homotopy category. And the other is, maybe it's called D plus of X. This is complexes of injective sheaves and homotopy classes.
When you say models, you don't mean those two are similar.
No, these categories are equivalent. What I'm going to claim is these categories are equivalent categories.
You have to inject and invert Quasi Isomorphisms. No? The top one first?
Yes.
You're right.
Well, let me, okay. Right, so the homotopy category of complexes with quasi isomorphisms inverted. So in other words, maybe I say a word about that. In general, when you invert quasi isomorphisms, you consider a sequence of morphisms where the arrows that go the wrong way are quasi isomorphisms. So you formally invert quasi isomorphisms. Okay. So I take homotopy classes, I take complexes of sheaves bounded below, I take homotopy classes of maps, and I now allow you to formally invert quasi isomorphisms. So that's the first model. The second model is simply homotopy, well, it's simply injective complexes and homotopy classes of morphisms. And the claim is that these are equivalent or isomorphic, I'm not sure what the word is, categories. So every object in K plus of X is isomorphic to an object in D plus of X. That's the statement that every complex of sheaves has an injective resolution. It's quasi-isomorphic to an injective. And so quasi-isomorphisms now become isomorphisms because they formally have an inverse. And any quasi-isomorphism in D plus of X has an honest inverse morphism rather than just a formal inversion, has an inverse morphism in D plus of X. That's the statement that a quasi-isomorphism between injective sheaves has a homotopy inverse, and therefore in the homotopy category has an actual inverse.
Could you explain that?
Sort of sequence with the arrows going both ways.
Yeah. So the simplest example of a morphism in a category where you've inverted quasi-isomorphisms would be to take A and a morphism to B or to C, and then a quasi-isomorphism from B to C. So if you're formally inverting quasi-isomorphisms, that means anytime you have a quasi-isomorphism, you formally put in an arrow the other way. That's called the inverse of this quasi-isomorphism. It doesn't exist. It's just a formal construction. So I just say that there's a morphism going back this way. So that would, by composing, give me a morphism from A to B. And I could keep going. Then I could go from B over to some C. I mean, I could have another quasi-isomorphism this way to C and then to D. And then. So any sequence like this, as long as the arrows that go the wrong way or quasi-isomorphisms, is a sequence of morphisms going the right way, which I can then compose to make a morphism from here to here.
You said something like it isn't there, but you can say it's there, and then all of a sudden it's there. I mean, what's...
Well, this is something you can always do. The question is, what do you get when you do it? And sometimes you get something reasonable, and sometimes you don't. It depends on the properties of the category and the properties of this collection of morphisms.
So these things like chain homotopic to chain homotopic or something.
Well, that's here they are. But if you have a quasi-isomorphism between two random complexes of sheaves, you don't know anything about trying to construct a chain homotopy inverse. I mean, there will not, in general, be a chain homotopy inverse.
That string of arrows that you asked about is, by definition, a map from A to B.
Right.
Map from A to B consists of those honestly existing arrows, but some of them go the wrong way.
Right. So as long as the ones that go the wrong way are the things you want to invert. I mean, this is like...
Homotopy between those things?
Sorry?
How do you define homotopy between those things?
Chain homotopy.
Chain homotopy, yeah.
It's always chain homotopy.
Yeah, but you include some long direction arrows, right?
Yeah, that's right. I guess, I mean, anything chain homotopic to a quasi-isomorphism is still a quasi-isomorphism. So you can take chain homotopy at every stage. And you'll still get the arrows going the wrong way will still be quasi-isomorphism.
Something more, right?
Yeah.
Because this guy happens to be an identity. You have to shrink it, and you can compose it. So it's kind of a bit I mean, this length is a kind of how many times this opposite direction arrows?
Any number of times.
Of this homotopy.
No, I think he's saying suppose you have a completely different morphism from A to B by a completely different chain of arrows. Then what would it mean for those to be?
You put a lot of identity, so they have the same length, and then you consider a vertical map.
Doesn't quasi-isomorphism mean that there exists a map since the composition is chain homotopic?
No, that's the problem.
I see. Okay.
But we want that to be
No quasi-isomorphism.
it induced an isomorphism on the homology sheaves, on the cohomology sheaves.
For chain complexes.
Let's agree.
Right. Well, for chain complexes of free abelian groups, those would agree. But I mean, even for chain complexes, right? There's this chain complex, and there's this chain complex, and there is a map in this direction, which induces an isomorphism in homology, but there's no map back. So if you allow non-free chain complexes, you'll see this same phenomenon. For free ones, it doesn't matter. I'm sorry, Kenji, I didn't quite get your point. Right.
Natural arrow and opposite arrow.
Right.
And you take chain homotopy of this one opposite arrow, so that it happen to be an identity.
Mm-hmm.
Then you can just shrink this.
Right, or turn it around and compose.
So you have kind of several process like this.
Yes.
So probably one need to check that this kind of things have good equivalence relations and.
Yes, well, all of that is going to be obvious once you use these injective sheaves and the fact that you really can invert quasi-isomorphisms down here. In some sense, I know this is going to give a reasonable definition only because secretly I know about this subcategory. In general, you don't know what you get. You may get a category where all morphisms are trivial.
Yeah.
You may not get anything reasonable. There are various axioms. Quillen has written down some axioms that.
So you can always get a category by this kind of inversion. It's a general fact.
Right, but what it is who knows?
Yeah.
But here we have a good. Okay. All right. Well, I promised you Flabby, so I want to now prove the fundamental theorem of sheaf theory. So this is something about sheaves because it's going to involve Flabby complexes. So the first theorem I need, which I don't think I'll prove, but it's proved the same way as for an individual sheaf. one can compute the hypercohomology of a complex of sheaves using a Flabby resolution rather than an injective resolution. So in other words, if you have a complex of sheaves bounded below, and you find a resolution which is a resolution by Flabby sheaves, so this is a resolution. So in other words, the vertical map between the complexes is a quasi isomorphism, and the Fi are all Flabby. Then the cohomology of the global sections of these Flabby sheaves with the map induced by D is identified with the hypercohomology of the original complex of sheaves. The definition of this hypercohomology was to take an injective resolution, take global sections, and calculate.
Does that be F instead of
R there?
Yes. And this is probably a star. But in fact, you can take a Flabby resolution. And the way I would prove this theorem is once I had a Flabby resolution, I would construct on top of it a double complex of injectives, which was a resolution of it, and then filter like I did before vertically, because Flabby sheaves have no cohomology except H naught. When you take that double complex and filter vertically and take global sections, filter vertically at E1, you simply get the global sections of this thing. On the other hand, it's an injective resolution of the Flabby complex and therefore of the original complex, so it calculates the answer. So the answer is given by the global sections, the complex of global sections of this thing. Okay. And now there is a particularly nice Flabby resolution of any complex of sheaves, the Gotamal resolution. So we've talked about, given a sheaf A, you make C naught of A, which is all maps from A, from X to the étalé space of A, no continuity assumption. Okay. And of course, A injects. Those are the continuous sections of the étalé space. This is all the sections. Okay. I then go to C naught of A mod A, and I do the same thing again. C naught of A mod A. I call that C1 of A. And so what I've done is I've embedded C naught mod A into C1, and I just keep going, and I make a complex which by construction resolves A, and also because I'm taking all possible sections, these are all Flabby. So it's a Flabby resolution of A, the Gotamal resolution. And this resolution has a beautiful property. A to this resolution is a functor from the category of sheaves to the category of complexes of sheaves, and it's exact. So if you have a short exact sequence of sheaves and you produce these complexes of sheaves, you get a short exact sequence. Well, by the iterative nature of the construction, we really only have to analyze the first step, or the first two pieces. So we have to show that A to C naught of A is exact, is a functor and is exact, and that taking this quotient, well, it's clearly a functor, taking the quotient is exact. So let's examine A to C naught of A. Well, anytime you have a morphism from A to B, you get induced maps on the étalé spaces, étalé of A to étalé of B, and therefore if you have a arbitrary section, continuous or not, of X into the étalé space, you can push it forward. So it's going to be a functor. It's clearly exact. Let's just see what are the stalks. The stalks are the direct limit as U shrinks and open sets that contain a point X, the product over Y in U of A, Y. Okay. Well, now if I had a short exact sequence of sheaves, that would mean the stalks all formed short exact sequences. Products of short exact sequences are short exact. And direct limits of short exact sequences are short exact. So this construction, starting with a short exact sequence, will produce a short exact sequence of stalks for C naught, and that's the definition that this is exact. Okay. You follow that? So we have AX to BX to CX to 0, or I should say Y maybe. Y, 0, is exact for all Y. That's this statement. So that says, take any open set U, product over Y in U, AY, product over Y in U, BY, product over Y in U, CY is exact. A product of short exact sequences is short exact. And then the direct limits. And so on are also exact. So products of short exact sequences are short exact, and direct limits of short exact sequences are short exact. So that implies that C naught A at X into C naught B at X into C naught C at X makes a short exact sequence, given that we started with a short exact sequence. Okay? So that shows you the first step in the construction is functorial and is exact. The next step in the construction is divide this one by A. That'll certainly still be functorial, and it will still give a short exact sequence. Because this is exact and this is exact. So that's what I have here, and now I take the discontinuous sections of this sheaf. Well, that's the same C naught construction again. So this was exact. So this is going to be exact, and I just keep going. So the whole Flabby complex is exact. So what that means is that now let's take a complex of sheaves. And let's resolve to get a double complex. Okay? So vertically, these are resolutions, and horizontally, they commute with taking cohomology, because this is an exact functor. So if I were to take cohomology in the horizontal direction, so if I were to take global sections and horizontal cohomology. So let's look at some place. Let's look at the sections of Cn of AP into sections of Cn of AP plus 1 coming from sections of Cn of AP minus 1. So I want to calculate the cohomology in the horizontal directions of global sections. Well, how do I want to say this? You see, the fact that C is exact tells me that when I go from AP to AP plus 1, and I look at the kernel, that C of AP into Cn of AP into Cn of AP plus 1 into the kernel of this map, C of D, the kernel of C of D, this is simply equal to C of the kernel of D. Cn, I guess it is. Well, kernel, it would be Cn of the kernel of D. That's the statement. That's the exactness of this functor applied to this short exact sequence. Right. So it commutes with short exact sequences. So the kernel of this map is C applied to the kernel. Likewise for the image, C of the image of D. So the sheaf cohomology here is simply C of the kernel of D over C of the image of D, which is the C applied to the cohomology of Cn applied to the cohomology. Nah. I'm having trouble today here. Should be C applied to the cohomology of A. I'm sorry. It's not working. Anybody help me out here?
Well, you don't need the upper script and what you're doing.
Well, that's picking out a row, that's all. Yeah, it's not varying.
Right.
I'm trying to do horizontal cohomology. All right, well, I'm going to owe you that too. I quit. All right, so I'm gone next week, the 5th, and I'm gone the 12th. But by the 19th, I'll have it all sorted out. Maybe I should just say what I'm trying to prove. I'm trying to prove when you take horizontal homology, cohomology, you get Cn of the pth homology of A. That's what I'm trying to prove. And now so that's taking horizontal homology. Now you take vertical homology. So you have this flabby resolution of the cohomology. So this is at E1, if you will, E1 in P. And then E2 in P will be the vertical cohomology of this flabby resolution. Well, that will just be the global cohomology of X with coefficients in the sheaf cohomology of the complex. So you end up at E2 with the global cohomology, the hypercohomology, well, hypercohomology of X with coefficients in this sheaf. That's at E2. And the whole thing, well, it's a Flabby resolution of the original complex. So at E infinity, you're converging to the hypercohomology of the complex A.
So the E1 doesn't look right. It's a, should be.
This, you say this is not right.
E1 is a sheaf, but E2 is a group.
Well, I'm sorry. Yes. Here, I've taken global sections, I guess. Right. And then when I take the cohomology, well, this is the global sections of a Flabby resolution, so it just produces the cohomology with coefficients in the sheaf that I've resolved, and the whole spectral sequence abuts to. So somehow this is, I haven't been able to say it, but these operations of taking CN, taking cohomology, sheaf cohomology, and taking global sections, and in this context where all our sheaves are Flabby, taking global sections is an exact functor, and these C's are exact functors. So I ended up with, started with the global sections inside here in cohomology, and I managed to pull everything out. But I can't sort of put it together right now.
The point that maybe you're missing is to say that exact functors can be taken cohomology.
That's,
right.
Of course, the point.
And that's a short exact sequence that has the 0, then the domain, then the image, and then the cohomology, and then 0.
Yeah, here. Right. So the kernel is the functor applied, sorry? No.
The cohomology is the last term before the 0.
Yeah, so I was using it again, right?
But it's not that short exact.
No, it's not this one. This one identifies the kernel with the functor applied to the kernel sheaf, and the image in C with the C applied to the image sheaf. Now I need the other exact sequence, image to kernel to cohomology, apply C to that to get this equation. But I don't quite see I don't see how the global sections are fitting in. I haven't got the global sections right yet. But this is called the local to global spectral sequence. It's special to sheaves. It doesn't have an analog in the general abelian category. And it says in particular, it says you can compute a spectral sequence which starts with the information of the cohomology sheaves and their cohomology and ends up at the global cohomology of A. So one consequence of this is that a quasi isomorphism induces an isomorphism in cohomology. Then the induced map in homology from the global cohomology, from the cohomology of A to the cohomology of B is an isomorphism, because this map will induce maps on these spectral sequences, and at E2 it's an isomorphism, so it's an isomorphism at E infinity, so it's an isomorphism. All right, I'm going to quit here. I owe you a couple of technical diagrams.